So it's when the rate of forward reaction equals the rate of backward reaction. So when the rate of forward reaction equals the rate of backward reaction, in a reversible reaction. So it's got to be a reversible reaction. So you've got many reactions which are reversible, and when you talk about a reversible reaction, it has to be reversible pretty much at the same time. There are a lot of reactions which can't be reversed at least at the same time. So one example that we can start off with is the example of water. And we can talk about a change of state where you have water liquid turning into water, turning into water vapors. So it's turning into H2O gas. Now this is a reversible reaction. It can happen at the same time. Like you can turn water, like water can evaporate. Like you have a closed water bottle, water can evaporate at the same time. It can condense back as well, pretty much at the same time. So that's an example of a reversible reaction. Another thing that you have to remember about this is, okay, when you talk about equilibrium, you're talking about the rate of forward reaction equals the rate of backward reaction. So we're talking about the speed of the reaction being equal. We're not talking about the concentration being equal. You could have more water molecules, less water vapors. I mean, the quantity of the substances could vary, but the rate of forward reaction equals the rate of, so the speed at which water vapors are getting formed and the speed at which the water vapors are turning back into water liquid, that speed has to be constant. We don't care what the speed is as long as the speed is exactly the same. So here's the first example, and the first example we'll discuss the Le-Chatelier principle, and we'll discuss how equilibrium is going to be affected by temperature. So that's, and what does the Le-Chatelier principle state about temperature? So here's my container, and that container has let's say it's a closed water bottle and it's got liquid water. There's H2O, which is in liquid state. And there are lots and lots of water molecules in there. Lots of them. Okay, so you got lots of water molecules, and we can just to increase the quantity just a second. So I've got lots of water molecules. Okay, they are all loosely packed, and things are not always at equilibrium. Remember this topic, equilibrium is always achieved. At a certain point, equilibrium is reached. So initially what will happen is that at this point, it's not at equilibrium because, I mean, there is no forward reaction, there is no backward reaction, but eventually what will happen is it's a closed water bottle. So some evaporation would start to happen, and some water vapors are going to be formed. So there's going to be a forward reaction, and water vapors will be formed. And once those water vapors start forming, and there's going to be a constant rate at which water vapors are forming, those water vapors have no place to go. So that means they would move around, they would collide with the walls of the container, and eventually they would lose energy and they would condense and they would fall back into the container. So that means there's going to be some reverse reaction that would start as soon as water vapors are produced. So every time a vapor is going to be produced, some other water vapor would condense and would fall back into the, it will fall back into the container. And this process would continuously repeat. Another water vapor would evaporate, and another one of them would sort of condense. So as long as the rate at which this is happening, rate of forward reaction and the rate of backward reaction is equal, that means an equilibrium has been established. Now, one of the reactions could probably speed up. I mean, things are not always at equilibrium. So there's a possibility that one of the reaction is favored or speeds up relatively. Whenever we talk about the term that one of the reaction forward or backward speeds up, it's a relative comparison. So maybe one of the reactions speeds up. That means every second, 3 molecules evaporate now. And every second, only one of them condenses back. Then the next second, 3 molecules evaporate. And the next second, only one of them actually condenses back. So what you can see is that the amount of water vapors are increasing. So that means the reaction is no longer at equilibrium because one of the reaction is much faster compared to the other one. So equilibrium is only when the rate of forward reaction and the rate of backward reaction is equal. So for equilibrium to be reached, it has to be a closed system. You don't want anything to escape. I mean, it's almost impossible to have equilibriums in systems which are open, where things can leave the container. So it has to be a closed system. Like this container, that's a closed system. You don't want, I mean, if your water vapors, they kind of escape, then they're gone. I mean, they've left the container. You can't reverse that. So things should not be able to sort of leave the container. They should always be part of the container. So it has to be a closed system. So coming back to temperature, this temperature thing. Right now, let's assume, and another thing about equilibriums is that the concentration of the reactants and the products, it becomes constant at equilibrium. The concentration or the quantity of the reactants and the products it becomes constant. Not equal, but constant. That means, I mean, you can have any number of water vapors, you can have any number of liquid water molecules, but the quantity will not change as long as it's in equilibrium. For example, every second, 2 molecules evaporate, and every second, 2 molecules, they condense back. So the quantity remains exactly the same. It does not change at equilibrium. So if I were to plot a graph of my reactants versus products for this specific example, the graph would kind of look like this. And I'm plotting the graph for this specific example. So here's my time. My reactants, I had a lot of water vapors. So let's say initially I had a lot of liquid water, H2O liquid. Okay, I'm just plotting what happened in this particular container. And initially, I had almost no water vapors. So that was 0. Then what happened? The amount of water vapors started to increase, and eventually there came a point when it became constant. I mean, that point indicated that equilibrium is now reached. So it's not changing. The amount of liquid water started to initially decrease, but then the reverse reaction kicked in, and the concentration became constant. It stopped. So it stopped changing. So that indicated that equilibrium has been reached. Now, these values, these lines could be anywhere. I mean, they could be higher, they could be lower, doesn't really matter. Like, for example, you could have, I mean, at a higher temperature, you could have a lot of water vapors and fewer liquid water molecules. So the height of the lines could be variable, but the graph would pretty much look something like this. So I'll just make, I mean, what this suggests is, I mean, this is the point. I mean, first thing is you should be able to, by looking at the graph, you should be able to identify that this is the point where equilibrium was actually, thoda sa aage kar lo, this one, where the values became constant. So this is the point where equilibrium was actually initially established. Let's say 1 second, let me. Afin, the concentration, remember the quantity, I mean, the ratio doesn't really matter. I mean, it's just that, okay, mujhe batao कि what will happen if the container is at a higher temperature? Eventually, there would be a lot more water vapors, right? Or here, let's say equilibrium is reached. And once equilibrium is reached, every second, one molecule evaporates, one molecule condenses back, one molecule evaporates, one molecule condenses back. So the amount would remain constant. It doesn't mean that the amount would be in any ratio. The amount would have, I mean, it could have any ratio. It doesn't really matter. Let's say you increase the temperature further. So you could have a lot more water vapors. Okay, let's say you're doing this at a very high temperature. So the amount of water vapors is a lot, or wo jo amount of liquid in it, that's gone down now. But even at a very high temperature, if it's at equilibrium, then every second one evaporates, one condenses, and so on. The rate of forward and rate of backward is equal. So the quantity could be any quantity. It will not have any specific ratio. Afiz, do you get my point? The only thing is, okay, whatever the quantity is, it's not going to change once equilibrium is reached. Is that clear?
Yes, sir.
Okay. So remember, the ratio of the products and reactants, it doesn't depend on this equation, the mole ratio. It doesn't depend on that. Okay. Let's say I decrease the temperature. I have this water bottle at a very low temperature. At a very low temperature, what would happen? There's going to be a lot of condensation. You'll have a lot of condensation, and तो सारे molecules जो है ना वापस आ जाएंगे. ठीक है, they will all start condensing. So the amount of liquid would be a lot higher. ठीक है, और थोड़े से ले.
So then constant का क्या मतलब constant मतलब कि मतलब अगर एक molecule ऊपर जाए तो वापस वही नीचे आ रहा है ऐसे?
हाँ, लेकिन it's not the same one. कि rate of forward reaction equals the rate of backward reaction. So let's say 1 second में there are 2 molecules that evaporated. और उसी second में कोई और 2 molecule they lost energy and they condensed, right? So the rate of forward reaction and the rate of backward reaction is equal. तो मुझे बताओ, the quantity does not change, right? पहले भी there are 3 and 3 6 molecules. Now you still have 6 molecules. Is that clear?
Yes, sir.
तो मेरा बस ये कि
लेकिन वो
हाँ,
अगर देखा जाए तो इसमें तो बैकवर्ड में भी क्वांटिटी वाटर की इंक्रीज है पर रेट हमारा कांस्टेंट हो गया ना.
हाँ, मतलब क्वांटिटी जो मर्जी हो, ठीक है. The point is कि
ठीक है.
you could have a lot of water vapors, you could have very few liquid water. You could have a lot of liquid water, you could have a lot of or very few water vapors. ठीक है, उनका आपस में रेशियो कुछ भी हो सकता है. ठीक है, मतलब that ratio has nothing to do with the equation. ठीक है, it has everything to do with the conditions that you're establishing the equilibrium at. लेकिन एक दफा equilibrium establish हो गया, then the quantity will not change. कि अगर 6 water vapors है ना, तो वो 6 ही रहेंगे. ठीक है, कि हर सेकेंड एक, लेट्स से 3 evaporate हुए and 3 other they lost energy and they condensed. Net
तो
result,
इसी को कांस्टेंट
हाँ, net result क्या है?
कांस्टेंट इसी को रेट को
क्या चीज?
सिर्फ कांस्टेंट हम रेट को ही बोल रहे हैं ना कि अगर एक इवेपोरेट हो रहा है तो वापस एक ही
हाँ,
नीचे आ रहा है.
लेकिन मैंने उसको भी कांस्टेंट कहा है कि I've also told you कि the concentration or the quantity of the reactants and products, it also becomes constant.
मतलब जितना ऊपर जा रहा है उतना नीचे आ रहा है।
हाँ, या जितने बन गए ना बस उतने ही रहेंगे अब, कि as long as it's at equilibrium the amount of water vapor will not increase or decrease. क्लियर है?
ठीक है सर।
मतलब रिएक्शन चल रहा है, वो evaporation is going on, condensation is going on, but it's happening at the same rate. ठीक है? So the point is, तो इसके ग्राफ्स देख लेना कि remember कि it doesn't, I mean the ratio, you could have a lot of liquid water molecules, you could have very few water vapors, ठीक है, or vice versa. लेकिन once equilibrium is established, then the quantity becomes constant. ठीक है, it no longer changes once equilibrium has been reached. अच्छा, अब नेक्स्ट चीज पे आ जाते हैं. You've got temperature now. What happens when you, इसी को देख लेते हैं. What happens now when you alter temperature, equilibrium gets disturbed. ठीक है, so changing temperature, so remember it has to be a closed system. Closed system, everything should be constant. Nothing should leave. So when you do any changes, when you change temperature, the equilibrium position changes. ठीक है, it changes. And the rule is, इसी के ऊपर एग्जांपल कर लेते हैं. The rule is, if you were to increase temperature, then equilibrium favors the endothermic side or the endothermic reaction. तो इसमें मुझे बताओ कि which one is the endothermic? ये water evaporation या water condensation? Which one is exothermic or endothermic?
evaporation एंडो होगी।
ठीक है. So the thing is, if you increase temperature, so let's say I've started burning a fire underneath it. I'm increasing temperature, I'm heating it up. So obviously there's going to be more. The rate of evaporation would be it's going to be a lot faster. ठीक है, and there's going to be कि अब पहले, let's say every second 2 molecules were evaporating, now 4 molecules are evaporating. And the amount of molecules that are condensing are fewer. Let's say only one condenses back. So now the rate is ये जो evaporation rate is much faster. ठीक है, it's a much faster
सर अभी
evaporation.
हमारा इक्विलिब्रियम डिस्टर्ब हो गया ना।
अब disturb हो गया. ठीक है, so remember when you change temperature, the equilibrium position changes. So now the thing is that equilibrium favors endothermic reaction. तो हम ये कह सकते हैं कि, so as long as you keep a higher temperature, there's going to be more water vapors that are going to be formed. So what you can say is equilibrium favors endothermic. That's the rule. Okay, we can apply that rule to any reaction. So if I have this reaction, कि वो container को छोड़ देते हैं, just write an equation, H2O liquid in equilibrium with H2O gas. So I keep on increasing temperature. Now it's going to favor one specific reaction, and that is the endothermic reaction, which is the forward one. ठीक है, वो endo है. So आप लिखोगे कि the equilibrium position now favors the product, or equilibrium position favors or shifts to the right side. Equilibrium favors products. You're going to get more water vapors now, or you can say that the equilibrium position, it shifts to the right side. So your equilibrium is now disturbed and it's favoring one of the reactions. And you can apply this rule to pretty much any reaction. And the reverse is also true. What if you did the opposite? What if you इसको heat करने की बजाय you started dropping temperature? So the reverse is, the other rule is, if you decrease temperature, तो क्या होगा? The exothermic reaction is going to be favored. Your equilibrium is going to get disturbed. पहले वो बराबर बराबर चल रहा था, now it's going to be disturbed. Decreasing temperature, equilibrium favors So equilibrium favors the exothermic reaction. And if you take this bottle and you place it in a fridge or a freezer, okay, you drop the temperature. So kya hoga? Now the rate of evaporation would slow down. Okay, it's going to be a lot slower rate of evaporation. The rate of condensation is going to speed up a lot. Okay, you start decreasing temperature, so there's going to be more particles that would be condensing. Okay, there would be more and more particles that would be condensing. So now the equilibrium is disturbed. The quantities are no longer constant. The amount of liquid is a lot more now. So when you decrease temperature, equilibrium favors the exothermic reaction, which is condensation in this case. Okay, you've got water, liquid, in equilibrium with water, which is water vapors. The backward reaction is the one that's exothermic. So you're going to have a lot more exothermic reaction. तो इसमें आप उल्टा लिखोगे the equilibrium position shifts to the left, or equilibrium favors the reactants. Or favors your reactants. So is this rule clear to everyone? Okay, what's the rule? Decreased temperature, which reaction is favored? The exothermic. Increased temperature, which reaction is favored? It's the endothermic. You've studied this in O levels as well. Okay, is this clear? Yes or no? Clear, Sidra, is this clear? Read, Oswa. So we're just going to apply this rule to different questions now. The first thing is, how do you figure out which one is exo, which one is endo? So if you have, so we'll just do a couple of examples. Okay, let's do the examples. The Haber process comes very frequently. So I've got N2 and 3H2. And it's in equilibrium with 2NH3. Now, most of the time, they don't actually tell you which one is exothermic, which one is endothermic. All they tell you is they just write delta H and they give a value in front of that. Let's say this one is minus 88 kilojoules per mole. So most of the time it's this. So most of the time it's this. Now, I said delta H, it's 2NH3. So the negative sign indicates, remember that negative sign indicates the enthalpy change is always given for the forward reaction. So whenever you see a reaction, it's got an enthalpy change, it's always given for the forward reaction. So that means the forward one in this specific case, you can't assume which one is exothermic, which one is endothermic. Always look at this. This one is negative. So that indicates that the forward reaction it's exothermic. And that vice versa also indicates that the backward reaction must therefore be endothermic. So you have to look at the enthalpy change values. Usse pata lagega which one is exo, which one is endo. Once you know that, then things are easier. Like if I decrease temperature, which reaction would be favored, forward or backward? क्या होगा?
Forward.
ठीक है, so whenever you decrease temperature, the rule is okay, the equilibrium is going to favor the exothermic reaction, which in this case is the forward reaction. So in this particular case, if you decrease temperature, then your equilibrium would go on to favor the exothermic, which is the forward reaction. So you always have to look at the enthalpy change values. That will discuss. So the first thing is you have to establish which one is exo, which one is endo, and then you apply the rule. Okay, don't just randomly apply the rule. First, figure out which one is exo, which one is endo. Let's do another example, and this time I've got. So let's do another example, and this time I've got carbon monoxide plus H2O. Okay, it's just a made-up reaction, and it's forming carbon dioxide plus hydrogen gas. I think this is balanced. Gas, liquid. This one is gas. This one is gas as well. And I'm just giving it a random made-up enthalpy change. Let's say this is plus 23 kilojoules per mole. And they're asking what will happen if you decrease temperature. What's going to happen if you were to decrease temperature? That's the question. Where would the equilibrium shift?
Backwards.
Okay, so it's going to shift backwards. Why? The first thing is establish which one is exo, which one is endo. So it's positive. That means, remember, it's given for the forward. So that means the forward is the positive one. It's endo. And that means the backward or the reverse one would be exothermic. So whenever you decrease temperature, it's going to go and favor the exothermic reaction. So backward or exothermic reaction is going to be favored. And the equilibrium position shifts to the left-hand side. What that means is that there's going to be more backward reaction. So you're going to get more carbon monoxide and more water molecules, and there's going to be lesser carbon dioxide and H2 gas molecules. So that's the first rule. Now, another thing with this rule and with the other rules as well is, and there's this, so that's our first rule. TK, you've studied this in O levels many times. TK, just remember, higher temperature, increased temperature, endo, decreased temperature, that's exo. Now, one very important thing about this is, okay, because let's do that later. Let's talk about pressure now. TK, I'll talk about that important point later on. So pressure would also alter the equilibrium. It will favor one of the reactions over the other one. The first thing is pressure only affects gases. That's the first thing. I mean, pressure has no effect on liquids or solid. Because gases are the only things that are compressible. A solid or a liquid has nothing to do with pressure, because you increase pressure, it remains exactly the same. Nothing happens to it. So gases are only compressible. So first thing, be very careful. If a reaction has only liquids, then this pressure thing is going to have absolutely no effect on it. Take one example is, let's say there's dissociation of ethanoic acid, and that's a reversible reaction. And all of them are in aqueous state. So in this particular case, pressure is going to have absolutely no effect on this particular equilibrium, because none of them are compressible, or they're not going to expand. If you decrease pressure, nothing would happen to them. They would just remain aqueous. So pressure has no effect in this case. सिर्फ और सिर्फ अगर gases होंगी only then will
तो इधर आपने एक गैस स्टेट दी हुई है
अच्छा नहीं सॉरी वो
पेज
गलत है,
पे।
aqueous लिखना है, ठीक है। So pressure is going to have no effect. इसका याद रख लेना कि be very careful with this, ठीक है। Only gases. अच्छा, how would it affect gases? So I'm going to take the same exact example and किधर गया उसी कंटेनर को उठा के लगा देते हैं यहाँ पे, just 1 second. So same water example. So let's pick this container. How would this container be affected if you increase pressure? So the first thing is, to increase or decrease pressure, you need a piston. You need a piston that would move, a movable piston which could alter your equilibrium position. Okay, so let's see, this is my movable piston, and now I'm going to increase pressure. Okay, and let's say that these are at equilibrium, and I'm going to start increasing pressure. How can I increase pressure? I'm going to push this downwards. So we are increasing pressure. So when you start increasing pressure, the particles in gas, nothing would happen to the liquid. The liquid is incompressible. So particles in gas are going to get compressed. I mean, nothing would happen to H2O, which is liquid. So there's lesser and lesser room for so now there's lesser and lesser room for gases to form. मैं pressure बढ़ाई जा रहा हूँ, ठीक है? What will happen is, if I continue to increase pressure, the particles would become closer and closer to each other, and there's going to be lesser and lesser gas. Eventually, you'll run out of room, so all the gases would have to change state. They would be so close to liquid water that they'll pretty much go into liquid water or change state because you don't have room for gases. So I'm confident, and now I can't increase pressure because now we have a liquid. So only gases were compressible. So the thing is, when you increase pressure, I mean, that's our rule. Whenever you increase pressure, what happens is you decrease volume. So volume decreases. And if you have lesser volume, less gas is going to be produced, or less gas mole side, or the side that has lesser gas is favored. Because you can't make gases. I mean, it's very hard because you're increasing pressure and there's no space left for gases to form. Vice versa, if I start decreasing pressure, if I want to decrease pressure, I would have to move the piston upwards. So now we are decreasing. So now we are decreasing pressure. So as soon as I start to decrease pressure, my volume increases. So I'm pulling the piston upwards slowly. So all of a sudden now, I've got a lot more gas particles. Sorry, a lot more room for gases to form. So there's obviously going to be more evaporation, and a lot more gas particles are automatically going to be formed because you've got a lot of room now for gases to form. So the other thing is that when you decrease pressure, the volume automatically increases. And now more gas can be formed. So the side that produces more gas, or the more gas mole side, is going to be favored. So the idea is simple, which is that increased pressure. You increase pressure, the volume decreases, and less gas moles would be, less gas would be produced. You decrease pressure, you take it upwards, the volume increases. Now you can have a lot more gas. So that's the simple rule. So increase pressure, less gas. Think of it, you're squeezing it, you're decreasing the volume, less gas would be formed. Decrease pressure, more gas would be formed. So if you have the water example, increase pressure, less gas would be formed. So it's going to turn into liquid. Decrease pressure, more gas would be formed. So it's going to favor the gas side or more gas mole side. Is this point clear? You clear है सारों को? So इसके ठीक है. Let's do more questions tomorrow on this. We'll probably finish the Chatelier principle. ठीक है. We'll do some past paper questions on this. तो कल continue करते हैं. ठीक है. Okay everyone. Allah Hafiz.